Study guide for the refraction quiz. Number 1. This is a double convex lens. Draw a ray diagram to find the location of the image. What happens to the image as the object moves closer to the lens? Okay, so the first line I'm going to draw is from the top of the object parallel to the axis and hitting the lens, and then that refracts and goes through the focal point on the other side. And then I'm going to draw a line that goes through the first focal point, and then that refracts to go parallel. And where these two meet, that's where the image is right there. Notice that the image is upside down, and it is reduced, it's smaller. And it's a real image. The light rays really do travel through that spot. Okay, now the object has been moved a little bit closer to the lens. So there's the first ray. And the second ray goes through that left focal point again. And here's the image there. Not much difference. We can't really tell what kind of changes have occurred from there to there. The object isn't that much closer to the lens. Okay, now it's significantly closer. Let's see what happens to the image here. This first ray doesn't change from one diagram to the next. It's always parallel and then going down from that same point on the lens. So the light ray is angling down at the same rate in each one of those three. It's this ray right here that changes. Hope I didn't draw that quite right. It should be a little bit steeper here now that it is closer to the focal point. And we can see now that the image is definitely bigger than before. And if we measure this, this is not as far as that. So it's farther away from the lens, and it's bigger. But it's still a real image, and it is still inverted. Number 3, this is a double concave lens. Draw a ray diagram to find the location of the image. What happens as you move it closer to the lens? Okay, so first ray is parallel to the axis, and it diverges. It goes away from the axis as if it came from that focal point there. The next one is going to go towards the focal point on the other side, and it gets refracted parallel. Okay, and these two refracted rays appear to have come from a spot over here. So here's the image here. It's very small. It is upright. It is virtual. The light rays really don't travel through there. It just appears that they do. Okay, the next diagram, the object is a little bit closer. The first ray is the same. It's going parallel to the axis, and then it diverges, or it hits the lens at the same point as before, because it's still the same height, and it diverges away from the same focal point. So these two rays are exactly the same as before. Okay, now the next one goes towards the right-hand focal point. Since the object is closer to the lens, this angle is going to be a little bit different. Not much here, but it is going to be some different. So this ray is parallel to the axis, just like this one, but this one's a little bit further up on the diagram than over here. And so that means that the image is going to be just slightly taller than the other one. Here's the image there. Okay, this one will be more dramatically different, because this, let's do it in the same order. We have the parallel ray, same height as before, same hitting the lens in the same spot as before, and it diverges away from the same focal point. So this angle up is the same as before. It's this ray that's going to be significantly different. See, it's angled at a different rate, so it's going to hit the lens at a different height. going to be higher up away from the axis yet again compared to this one. We can easily see. And so this looks like it came from an image here. It's going to be a little bit closer to the lens, and it's going to be a little bit taller. Finish the ray diagram and answer the questions. Finish the ray diagram to find the image. The image is, okay, so this is double convex, and so it's going to refract the light rays downwards like that. And then the second ray goes through the focal point, hits the lens, and refracts parallel. And so here is the image right there. The image is real because the light rays really do travel through that spot. The image is upside down. Number 7. Finish the ray diagram, find the image. We just did that. The image is how many centimeters on the, okay, this is going to be the right side. And I don't have a ruler with me, so I can't say exactly, but from here to there, looks like it's about 3 centimeters. That's an approximation. I don't have a ruler with me. But that's how you do it on a quiz. I'll give you rulers on the quiz. Number 8. Finish the ray diagram at the top and find the image. Okay, so this is a diverging lens. We can see that as we go from the axis up, the sides are getting farther apart. So that's my clue that the rays are going to spread apart when they go through this. So here's the spreading out ray. It's going away from the axis. And the next ray goes from the top towards the other focal point, and it gets refracted to be parallel. And these two rays appear to have come from one spot over here somewhere. Let's trace them back and see where that is. So right there is the image. Okay, this image is virtual because the light rays really don't actually pass through that spot. It just appears. We have to use our imagination in order to think of a single spot here where the light rays come away. Finish light ray at the top. The image is right side up. The crisscross is above the axis, and so we know that it's going to be right side up. Finish the ray diagram at the top of the page and find the image. The image is, okay, so it's between the left focal point. Here's the other focal point. This would be the right one. This is the left one. It's between the left focal point and the lens. Number 11, the index of refraction of water is 1.33. The index of refraction of glass is 1.65. A beam of light goes from the water into the glass. The angle of incidence is 30 degrees. That's this one right there. Find the angle of refraction. So we're going to use Snell's law. N1 is the index of refraction for the first material, which is water, and we're given that to be 1.33. Sine, the angle in the first material is the 30. Remember, you always use the angle between the ray and the normal, not the other one. Okay, N2 is the index of refraction for the second material, which is glass here. It's going from water into glass, and we're given that that's 1.65. And we are looking for the second angle. Okay, I need to go and get my phone for its calculator. Okay, so we type in 1.3, delete, 1.33 times the sine of 30 equals 0.665. Okay, and now I'm going to divide both sides by 1.65. I get 0.403 is equal to the sine of theta 2. Now I don't want to know the sine of the angle, I want to know just the plain old angle. So I take the inverse sine of both sides. So I'm going to hit inverse, inverse sine, there we go. 0.403 equals, I get 23.7. Next, a beam of light goes from a new type of plastic into water. The index of refraction for water is 1.33. The angle of incidence is 50 degrees. The angle of refraction is 85 degrees. Find the index of refraction for the plastic. Okay, Snell's law once again. The first material is shown over here to be the plastic. That's the index that we're trying to figure out. So it stays a letter. The angle over here is 50. The index of the second material is the index for water, and that's 1.33. And the second angle is shown to be 85. On the right-hand side, we'll multiply 1.33 times the sine of 85 equals 1.32. And the sine of 50 over here, the sine of 50 is 0.766. Divide both sides by 0.76. So 1.32 divided by 0.766 equals 1.72. Number 13. A double convex lens is used to focus an image of a candle. The candle is 20 centimeters from the lens. The image is on a screen 10 centimeters from the lens. Find the focal length. So we're going to use this equation, the Fedoti equation. The F is what we're trying to find, the focal length, so that stays a letter. DO is the object distance. In this case, the glowing object is the candle, 20 centimeters. And the DI is the image distance. The image is on a screen 10 centimeters away. So, with this kind of a lens, everything is positive. We're going to change these into decimals. So 1 over f is 0.15. But I don't want to know 1 over f. I want to know just a plain old f. And so I got to flip this side. Well, if I flip that side, I have to flip this side as well. So that gets me to f is equal to 1 over 0.15. So let's see here. 1 divided by 1.5. Nope, that's not right. 1 divided by 0.15 equals 6.666. We'll round that to 6.67. Number 14. Double convex lens is used to focus an image. The object is 25 centimeters from the lens. The focal length is 5. Find the distance to the image. So we're going to use the Fedoti again. but this time we're looking for the di. The F is 5, DO is 25, changing to decimals, this is 0.2, this is 0.04. Subtract off 0.04 from both sides. And then we have to flip that side to get the plain old di, so that means I have to flip this as well. And this is going to be approximately 6. When a light wave enters a material with higher density, you can think of that as it's harder for the light to go through. So it's going to slow down, it's going to get a lower speed. It is going to bend to a smaller angle. When light goes into a lower density material, it's going to speed up. So it's going to get a higher speed, so it's going to bend to a higher angle, a bigger angle to the normal. A medium, that's the term for the material that the wave is in. Whether it be a sound wave, an earthquake wave, an ocean wave, or a light wave. When a wave hits a boundary, it can do 3 things. Some of it can reflect. Some of it can refract, perhaps, and some will be absorbed. When we have a boundary like between air and a brick, light is not going to refract into the brick at all, but it will reflect, and the brick will get warm, and so that shows that it's absorbing the energy. Number 19, use the lens equation to find the exact location of the image. Lens is double convex, football shaped, and that means that everything's going to be positive. The focal length is 10. The object is 15. Okay, so we're going to use the Fedoti equation, and the next one is going to be it's going to be very similar, but it's hourglass shaped, so that means that there's going to be some negative. Okay, so let's do number 19 over here. Let's see here. We have Fedoti. We want to find, let's see here, location of the image. So we're looking for DI again. DO, the object, is 15 centimeters. And the focal length is 10. So that's 1/10 plus 1 divided by 15, 0.066. I'll just put down 0.06 for simplicity's sake. 1 over di. Subtract off 0.06 from both sides. And then we have to flip both sides. So we have 1 over 0.04 is equal to di. And let's divide that out. 25. Okay, now the next one is an hourglass shape. So we're going to have some negatives involved. Fedoti, 1 over f equals 1 over do. I'm kind of cheating there with my mistake. And 1 over di. So the focal length is going to be negative. Let's see here. Image length is 20. So that's going to be a negative 20. Object distance is 15. And we're looking for the f. Okay, so 1 over f is equal to, let's see, this is 0.06. We figured that out a moment ago over here on this side. 1 over 20 is going to be 0.05. is 0.01, so f is going to be 100. And that's the end of the review for the refraction quiz.